Hello, we have gone over some material on reciprocal lattice. So, in today's class we are just going to look at 3 worked examples about how you would go about drawing a reciprocal lattice based on the few rules that we have understood about the reciprocal lattice. Okay. So, the 2 major rules that we put down are the 2 rules that I put down here. We said that the reciprocal lattice vector is designated as HKL and that this is perpendicular to the plane HKL. So, in real space you have the plane HKL, the reciprocal lattice vector, which is a vector in reciprocal space, is perpendicular to the plane in the real space. Okay. So, this is one rule that we put down for that we derived, and we found that given our the way we were defining reciprocal space, the way we were defining our reciprocal lattice vectors, this was one relationship that we arrived at. The other relationship that we arrived at is the modulus of this vector. So, we said the modulus, or we found that the modulus of HKL is equal to 1 over the spacing of DHKL, or 1 divided by the spacing of DHKL, right. So, these 2 rules we arrived at, and we just looked at a general triclinic cell. So, A was not equal to B, not equal to C, and the angles were all could have been any angle. So, there was no great specification on the cell. So, these rules are general. So, based on this we will do 3 worked examples. So, the first example we will do is this. We are going to, our problem is basically this. So, we would like to draw the reciprocal lattice of a cubic cell, of a cubic lattice, and we will use a 2-dimensional representation of it, meaning actually it is 3-dimensional, but we are looking at it from the A3 direction, and therefore, you only see the A1 and A2 axis. So, as seen through the A3 axis. Okay, so, this is our problem. So, this is the example that we are going to look at. We would like to draw a cubic lattice and we were going to draw it along the as seen through the A3 direction, in other words perpendicular to the A1 and A2 directions, and for that we would like to draw the reciprocal lattice. So, now as you know, for a cubic lattice A1 equals A2 equals A3, the modulus of these 3 vectors is the same, and alpha equals, so this is the modulus of these 3 vectors is the same, alpha equals beta equals gamma equals 90 degrees, right. So, this we know about the cubic lattice. So, we will draw the cubic lattice here, and we will make some assumptions on the dimensions of A1 and A2, and then on that basis we will come up with the reciprocal lattice. So, let us just draw the cubic lattice as seen. We will assume A3 is perpendicular to the plane of the board. So, we see A1 and we see A2. Okay. And A3 is perpendicular to the plane of the board. So, we simply draw a circle here indicating that A3 is there, but it is perpendicular to the plane of the board, right. So, now we will complete this lattice. So, we just take, so this is how it will be. So, it is a cubic lattice, and then you can add additional points to fill up the space, right. So, now we also learned that through our definition that if you go back to what we defined here, we have HKL is perpendicular to 1 by DHKL, and HKL I am sorry is equal to, modulus is 1 by DHKL, and the vector itself is perpendicular to HKL, and therefore, we found that so for example, if we have A1, A2 and A3 as the real lattice vectors and B1, B2, B3 as the reciprocal lattice vectors, we had B1 is perpendicular to A1 and A2 and A3, and similarly B2 is perpendicular to A1 and A3, and B3 is perpendicular to A2 and A1, right. So, this is how you would get these things based on these relationships. So, that is how we have defined it, because it is A2 cross A3 by the volume, A1 cross A3 by volume, and A2 cross A1 by volume. So, given that, it is naturally perpendicular because of the way we have defined it. So, now we come back to our worked example. So, we would now like to draw a lattice which is B1, B2 and B3. So, we see B1 is perpendicular to A3 and A2. So, that means it is perpendicular to the A3 axis is here, A2 axis is here. We will assume that these are all about let us say 2 angstroms, which is a very reasonable approximation for many materials. So, we will assume that the dimension A2 is 2 angstroms, this is 2 angstroms. So, on this scale, if you look at the idea that so first we will look at the directions, so, and then we will look at the magnitude. So, our directions are like this. The B1 axis is perpendicular to A3 and A2. So, A3 is perpendicular to this plane of the board, A2 is here. So, the B1 axis is along this direction, B1 axis is along the A1 direction that we have here. So, I will just draw the B1 axis here, I will take another color here to make it clearer for you. So, this is a real space here and this is reciprocal. Okay. So, now along the A1 direction is also B1. So, we have not put a magnitude yet on it. So, this is B1, this is the direction of B1, and then B2 will be perpendicular to A1 which is here and to A3 which is in this direction. So, B2 is along that direction which is similar to the direction of A2. So, B2 is along this direction. Okay. So, we got the directions right based on the idea that it is perpendicular to those planes. The other thing that we know is the value of the reciprocal lattice vector is 1 over the spacing of those corresponding set of planes. So, the spacing between these planes is 2 angstroms right now, that is the lattice spacing. So, that is also the spacing between these set of planes, it is the spacing between these set of planes. So, therefore, the B1 and B2 and B3 are all going to be inverse of 2 angstroms. So, that is 0.5 angstrom inverse. So, this is 0.5 angstrom inverse, and similarly this is 0.5 angstrom inverse. Okay. So, if you did that, you can just complete this diagram, and so you would get and similarly B3 would be here in the same manner, that will also be 0.5 angstrom inverse. So, they have not drawn, actually they are in different units. So, I have not drawn them both to the same scale, but the point is this is 2 angstroms across, this is 0.5 angstrom inverse. So, that is the point, and in normal labeling the way we do it is this is simply called 1 0 0 without any brackets, this is called 0 1 0, this would be 1 1 0 and so on. So, you can add, actually you can add the next point also if you wish, and this would become this will be 1 2 0 and this is 0 2 0. So, like this you can add additional points, and so that is how you would generate the reciprocal lattice of a cubic real lattice, the reciprocal lattice corresponding to a cubic real lattice, right. So, we have now taken a specific case and we have done a worked example on how you would take a lattice and come up with a reciprocal lattice. We will do a similar example also similarly laid out, except that we will relax some conditions here, so that this has made it convenient for us because they were all perpendicular to each other. So, we will make it a little bit more difficult for us by relaxing the conditions on the lattice and then see what we get. So, we will now look at a hexagonal lattice. So, a hexagonal lattice has the following conditions. You have A equal to B not equal to C, and we have alpha equals beta equals 90 and gamma equals 120. So, this is the description we have for a hexagonal lattice. So, let us just draw that axis, axis, and again we will assume that the C axis is perpendicular to the plane of the board. We will assume that. So, that is the same as A3 axis that we would say A1, this would be A1, this is A2, A3. We will assume A3 is perpendicular to the plane of board and A1 and A2 are along the plane of the board. So, we will simply have this here, I will put something down here, we will say this is 120 degrees, right. So, you will have so that actually yeah. So, we will have A1 and then we will come here, this is A2 and this would be A3. Okay, so, that is how we would do it, and incidentally this would then be a right handed system. So, actually even here we would have to this is a cubic lattice, so here it did not matter as much, but technically this would have to be a right handed system. So, we should actually have marked this as A1 and this as A2, but our basic processes would have been the same. So, similarly this would have become B2 and this would have been B1 to keep it right handed. So, just to keep it right handed, that is what it would have been, but basically it is still all cubic, so it does not really matter here in any great significance in terms of our result, but here also we will look at it the same way, a right handed system. So, we have A1, A2 and A3, right. So, they are all the same, A1 and A2 are of the same magnitude, this angle here is 120 degrees. So, let us just complete this drawing this at least this unit cell of this lattice. So, it will be like this. So, this is the unit cell we have. Now, when you want to draw the reciprocal lattice of this unit cell, the same ideas will hold true. So, we now have the B2 axis as being something that is perpendicular to A3 and A1. Okay. So, what is the perpendicular direction here? The perpendicular direction is in this direction, right. This direction here is perpendicular to this A3 and A1 is form this plane, A3 A1 plane. This is the direction that is perpendicular to it. So, it is in that direction that we will have the B2 axis. So, we just put a dotted line here to just imagine it for ourselves, and then we just draw that line here. So, that is the direction of the B2 axis, the B2 axis which is perpendicular to A3 and it is perpendicular to A1. Similarly, if you look at the B1 axis, the B1 axis is perpendicular to A3 and A2. So, it will actually appear in this direction, right. So, parallel to that we will draw a line here, that is the B. So, this is the B3 sorry this is the B1 direction and that is the B2 direction. Okay. So, B2 direction is that side and B1 direction is this side. Now, magnitude again we have to see, we will have to make some assumption for interplanar spacing here. So, let us not worry about the lattice dimension directly, we need to worry about the spacing. Spacing between the planes is the perpendicular distance between these planes, and so we will just assume that that is say 4 angstroms, we will assume that the planar spacing there is 4 angstroms. So, if you assume that the spacing here, if you assume that the D for example D100 is equal to the spacing of the 100 planes is equal to let us just say 8 angstroms, let us just say 4 angstroms. Okay. So, then the reciprocal lattice is going to be inverse of this. So, that is going to be 0.25 angstroms. So, you will have a reciprocal lattice here where if this is the origin and B3 again would be perpendicular to this. So, this is actually 0.25 angstrom inverse, that is the spacing of that vector. Okay. So, this is B1 and similarly similar dimension you would have here is B2 would come up to here and then you can complete the lattice. So, you can just extend this and you can extend this. So, this is now the reciprocal lattice of a hexagonal cell and you can extend it. Of course, once you get once you get 2 vectors you have actually you have it is a 3 dimensional structure of which we are seeing one planar view, we are seeing it face down with this along the B3 direction and that is why you are seeing it like this. But basically once you get the 3 basic vectors which is B1, B2 and B3, you can actually draw the rest of the lattice. So, you can extend here, get the next point, you can extend here, you can get the next point. So, you can see additional points would appear here, this would be a point, this would be a point, and you can label them exactly the same way we labeled before. So, this is B1, so this is 100 and it is just written that way without any brackets. This would be 200, this is 010 this is 0 2 0, right. This is 1 1 0, this is you go 1 along this direction, so 1 2 0, this is 2 1 0, and this is 2 2 0. Okay. So this is how you would now get the reciprocal lattice. You are getting the reciprocal lattice of a hexagonal system, wherein you have taken one view of it, which is convenient for us, which is you are looking down the A3 axis, and therefore you have gotten this. Similarly, you would have the real lattice spread across space. That is how the reciprocal lattice is spread across space. So you see between this example and the example we did here, which is a cubic cell, and there you have done a hexagonal cell, we see that the two rules that we had, which is that the HKL is perpendicular to the plane HKL, and the modulus of HKL is 1 by the or 1 over the spacing of DHKL. So given those two rules, the geometry and layout of the lattice we have been able to show here in these two worked examples, and in principle you can extend this, right. What we will do is we will do one more worked example where we will try to complicate it a little bit more further, we will basically try to look at a 3-dimensional structure and see how best we can manage to draw something. So that at least we understand that it is not an impossible act. You can actually do it, and certainly if you had the right kind of software, you could probably do it a lot easier than what we are doing on the board. So what we will do is we will take a triclinic cell, we will try to set something up in a 3-dimensional sense, and then using the two examples that we just did, using what we have learned from there, we will try and solve and see if we can draw the reciprocal lattice corresponding to the triclinic cell. So to begin with, we will draw a triclinic cell. So a triclinic cell, as we already saw in our class, has the general restrictions or lack of restrictions, I would say. A is not equal to B, is not equal to C, and we have alpha is not equal to beta, is not equal to gamma, is not equal to 90 degrees. So basically all 3 axes could be any length, the angles could be anything, right. So that is our most general case. So if we are able to draw something for it, presumably we can always work our way back to drawing it for anything that is less, has less variation in it than this has. So we will just draw something here and work our way through it. So this is one triclinic cell. So this is A1, this would be A2. So just to make it easy for ourselves, we will assume that A1 is the longest of them all. A2 is let us say it is half as long as A1, and A3 is half as long as A2. So we will have A1, A2, so right handed A1, A2, and then A3 is up here. Okay, so we will just complete this diagram. So you will have something like that. So something like this. So this is our diagram of a triclinic cell where A1 is not equal to A2 is not equal to A3, and the angles are not all 90 degrees. In fact, they could be anything, they could be basically anything. So we will follow the same logic, we will first figure out the directions, then we will try to put in the modulus and so on. We will just make some assumption here, we will simply say that the D100, which is along the A1 direction, we will simply say that that is 8 angstroms. We will say D010 is 4 angstroms, and D001 is 2 angstroms. We will make some assumption like this, and then we will see what best we can do with it. So therefore, if you see here, we need to have the B3 direction has to be perpendicular to A1 and A2. So it means it will be straight up. So the B3 will come something like this. That is the B3 direction. So let us just put down the directions first. B3 is perpendicular to those two. so the B1 direction will now have to be perpendicular to A3 and A2. So that plane is facing like this. So the perpendicular would come somewhat in that direction relative to this plane. Relative to this plane, this is the direction in which the perpendicular would come. So we will just draw the perpendicular like that. So that is the plane that is perpendicular, that is the direction that is perpendicular to this plane. So we just make it perpendicular. And then finally we would need to pick one more plane here, which is the A3 and A1 plane, and the perpendicular to that is headed off in that direction. So we will just draw that there. So we now have the three directions which are all perpendicular to those respective planes. So they meet that criteria that HHKL is perpendicular to the plane HKL. So that criterion we have got. Now we need to know something about the dimensions. So we have B3 in this direction and it has to be 1 over the spacing of the 001 planes. 001 planes is 2 angstroms. So 1 over that is 0.5 angstrom inverse. So just to make it convenient for ourselves, we just make the scale large enough so that we can draw it conveniently. We will just call it, say that this is 0.5 angstrom inverse. So this is B3 up to here. Okay. Then B2 we will see, B2 is actually 1 over the spacing 4 angstroms. So it is 0.25, so that would be half of this. And so B2 is now going to be in the direction, this direction here. So that is we are going to have 0.25. So about half this magnitude here, half this magnitude here is what we will put here. So that is B2. Okay. So that is 0.25 angstrom inverse. And finally, we have to have this particular direction. In this direction we have 8 angstroms. So it is going to be 0.125 angstrom inverse, which is half of this, and so that is roughly this distance. So about half of that you just translate it here. So B1 is here, right. So we have B1. So I'll just put it down here. B3, modulus of B3 is 0.5 angstrom inverse. B2 modulus is 0.25 angstrom inverse, and B1 is 0.125 angstrom inverse. So we have got ourselves the 3 values, we have got the 3 directions. So now it is just a matter of completing the lattice. So we simply have to draw those, finish the lattice, so complete the lattice. So draw the lines that are parallel. So there you go, we have the reciprocal lattice. We have reciprocal lattice, so this line goes all the way down here up to here. So that is the reciprocal lattice corresponding to this real lattice, which is a triclinic, very generic triclinic lattice, and we have simply used those rules that we have discovered or arrived at through our discussion on the reciprocal lattice. And as you can see, one of the things that you immediately notice is that whatever is there in real space is getting inverted into reciprocal space. So larger spacings in real space become smaller spacings in reciprocal space. So you have an inverse relationship, and that is why it is called reciprocal space. So 8 angstroms becomes the largest axis there, something corresponding to that becomes the smallest dimension here, the smallest dimension here, something corresponding to that becomes a largest dimension relatively speaking. Of course, these are in different units, this is angstrom inverse, this is angstroms. So, they are not necessarily drawn to the same scale and shown here, but the geometry is what is important. The geometry indicates to you what is going to happen. The units are with respect to that respective figure. So, that is how we go about it. So, right. So, with this we will conclude these worked examples. I think they would give you an idea of how we would go about constructing a reciprocal lattice given some specifications for the real lattice. Okay. I hope these 3 worked examples illustrate that to you. Thank you.